Imagine you're strapped to a big chunk of metal which is being raised over 120 meters, which then nosedives, followed by butterflies in your stomach. Now, when you put it that way, roller coasters sound terrifying and exhilarating at the same time. And according to us, this is the perfect topic to integrate physics into day to day life, with amusement rides being loved by people all around the world. Now, before we begin explaining the physics of a roller coaster, let's first understand where it all started from.
The initial concept of roller coasters can be traced back to 18th century Russia, dubbed as the Russian mountains. In winters, the snow-packed mountain slopes were sprayed with water to create a slippery surface, whereas in the summers, wheeled carts were used to go down the ramps, creating the same effect. In 1817, the world's first ever full-circuit roller coaster was constructed. Businessmen were quick to take the idea of riding carts down the slopes and commercialized it. In 1884, Lamarcus A. Thompson constructed the iconic switchback railway at Coney Island, New York. Despite being only 15 meters tall, the switchback railway was highly popular and ushered in a new era for roller coasters in the United States.
The underlying principle of all roller coasters is the law of conservation of energy, which implies that energy can neither be created nor be destroyed. It can only be transformed from one form to another. In this video, we'll be talking about mechanical energy, potential energy, kinetic energy, force of gravity, mass, and speed. There are broadly two different types of roller coasters. The difference in them primarily depends on the way they are launched. One uses potential energy, while the other uses mechanical. Most roller coasters start off with something called a lift hill, which mechanically lifts you to the top of the first hill. The train accumulates more potential energy as we go higher up. But the other type of roller coasters start a little more suddenly. They're rapidly propelled forward thanks to the hydraulic launch system. Hydraulic launch systems work by using a cable that is attached to two important pieces: a catch car, which connects to the bottom of the roller coaster train, and a giant winch, which is basically a huge spool that winds the cable when it is turned by some motor. So, to launch the train, this cable pulls it down the tracks really fast. After a few seconds, the catch car releases the train so it can accelerate up the big hill. The hydraulic fluid and some nitrogen gas are separated by a piston inside this chamber called the hydraulic accumulator. The hydraulic fluid used is incompressible. Then this fluid is pumped into the accumulator and compresses the nitrogen gas so that there are more gas molecules bouncing around in a smaller space, which increases the pressure. Nitrogen gas is used because it's cheap, easily available, and does not cause huge explosions. And once the pressure is high enough, a valve is opened and the hydraulic fluid rushes out to power a bunch of motors which turn the winch and pulls the cable and accelerates the train. Just like that, within a couple seconds, you're speeding along at hundreds of kilometers per hour. During the launch process, if enough energy is not produced, the train might not make it over the hill, and this is called a rollback.
Now, as both the trains reach the peak of the first hill, the potential or mechanical energy in them gets transformed to kinetic energy due to the law of conservation of energy. This kinetic energy, or the energy due to motion, drives the train down the first hill and reaches its fastest speed. The more speed the object has, the more kinetic energy it possesses. As the train climbs up the second hill, it begins to slow down as the force of gravity acts on the train. It is for the same reason why we fall back to the ground when we jump in the air. The train begins to travel slower and the kinetic energy transforms to potential energy. This constant pattern of energy conversion continues throughout the ride. Now, as the ride continues, some amount of energy is lost due to friction created and heat produced by the wheels running on the tracks. Along with friction, wind resistance, which is the air pushing against the train, slows down its movement. This is why the rearmost hills, or the hills located at the end of the roller coaster, are smaller than the first ones. Now, let's see how the mass of a roller coaster affects its speed and energy. So the more mass, the faster it travels, because mass increases both potential and kinetic energy. This is why they ensure that all seats in a roller coasters are occupied. Heavier train with more mass carries more energy and completes the track faster than a lighter train with less mass. You can see how train A is faster because of more mass than train B. So, to conclude, this is how roller coasters rely on a mix of mechanical, potential, kinetic energies, force of gravity, mass, and speed.
Coming to the future perspective of roller coasters, we have virtual reality and magnetic levitation or maglev. By leveraging VR technology, there is an opportunity to integrate VR experience overlays with existing roller coasters. While VR additions to roller coasters were introduced in 2015, the adoption rate is high. VR uses an untethered headset that utilizes a smartphone to display a 360-degree virtual world. VR coaster has a black box mounted on it, which picks up the rotation of the wheel, location, and other data and sends the information to each headset. What's truly remarkable is that even though every guest is having the same experience, the timing of what the guest sees varies depending on where they're sitting on the roller coaster. Imagine if there was no friction at all. What if there were no rails or wheels? What if electromagnets propelled the cars? This is the idea behind the maglev technology.
This roller coaster would include a cushy ride, incredible speed, free falls, underground tunnels, water diving, and heart-racing turns and loops.
This system of train transportation uses two sets of magnets, one to repel and push the train up off the track, and another to move the elevated train forward. Taking the advantage of the lack of friction, a 6-foot wide transparent sphere replaces the traditional open top car. Gyroscopic technology would let the sphere roll along the tracks without letting the riders get exposed to dangerous G-forces.
A gyroscope is a device with a wheel that spins, having angular momentum similar to a stone tied to the end of a string.
A wise man once said, "With great physics projects comes great limitations." And these limitations are one hell of a roller coaster to go through.
In 1888, the Flip-Flap Railway became the world's first inverting roller coaster, allowing riders to go upside down through a tight circular loop. However, this design ride was flawed. The circular nature of the loop caused the riders to be subjected to intense G-forces, which resulted in many people blacking out during the ride. It was this design flaw that delayed the widespread use of inversions for many decades to come. Another common limitation faced by the roller coaster is rollback. As explained earlier, when the cart does not attain an ample amount of potential energy, it causes the cart to decelerate due to the force of gravity, hence making the cart unable to climb the first hill, which is why it's important to provide the cart with enough potential energy.